This is 5.2. I think I can pause this as we go. So 5.2. Basically, this is a continuation from last week where we talked a little bit more about functions and explained them in a little more real-life situation or kind of a better way for you guys to understand them. Today is I think it's the 30th, isn't it?
Yeah.
So January 30th. So, yesterday we talked to you guys a little bit about definitions. We talked about domain and range. We talked about relationships, and more specifically, we focused on a function. Do you guys remember what the definition of a function was? It's a special relationship where each domain has exactly one range. So, we're going to put that on the spot a bit more with today. We're going to talk a lot more about functions. And you could think about it like a little black box, where when I have an input, my function does something to the input, and it spits out a specific output. Okay? And no matter, if I have the exact same input every single time, it should spit out the exact same output every single time. If it does that, it's a function, right? For every domain, everything I put into it, I'm expecting a result when I pull it out. If I put in, $5 into the vending machine and I get a bag of chips, every time I put in $5, I should expect a bag of chips. The one time I put in $5 and I get 2 bags of chips, something's weird. It's no longer a function. So, in this situation, our relationship is going to be the distance from Edmonton. Because most of us, on average, have at least driven to Edmonton once or twice in our lives. It's something tangible we can all kind of figure out. So when you start the drive from our school right here, we're basically at 0 time. Now this is also a really tricky one because when it comes to speed, there's a couple of variables we don't count for the fact of this is assuming you're going the exact same speed the entire time. You're going through Taylor at 100. You're going up the hills at 100. You're going down the hills at 100. You're going through Grand Prairie at 100. There's no slowing. There's no stopping. There's no red lights. You are at constant speed. Okay. How far away is Edmonton from Fort St. John?
600 kilometers.
Close. What is it?
829.
No.
749.
No. You're just spitting out numbers.
Those were both pretty awesome guesses, though.
No, they were not. It's about 703 kilometers from our spot here. It depends what part of Edmonton you consider. If you're looking at the outskirts, probably close to 600. I'm thinking downtown Edmonton. In fact, I'm looking at my old house because I'm on Google Maps. It was like 703 kilometers from my parents' house to my house in Edmonton. So, at 0 minutes, if I put an input of 0 minutes, the output is going to be the distance from Edmonton. It's 703 kilometers. Okay? To make life easy, we'll probably say closer to 700. After 30 minutes of driving, I'm going to be 650 kilometers away from Edmonton. Again, this is kind of assuming I'm going exactly 100. There's no issues whatsoever. There's no stop signs. After 2 hours, right? A 2-hour input, I'm now 500 kilometers away from Edmonton. Right? If I started right now and drove for 2 hours, I'd be 500 kilometers away. If I started right now and drove for 1 hour, I would be 600 kilometers away. So whatever my input is, there's a distinguished output. Is this a function?
Yeah.
Yeah, absolutely. And what you guys have to do is kind of write up some sort of frame for this that you could explain it as a formula. So we're definitely talking about distance. I want to say the distance is going to equal, what's our total distance? Technically 703. We're going to round that, and we'll just say 700 just to make the math really simple. So 700 minus, if we're going 100 kilometers an hour, no matter what time we're dealing with, as long as it's in hours, it's going to be 100 times our time. Is this written in function notation or two-variable notation? Heard someone say it. Say it louder. You're correct. Oh, it's over here. It's two-variable. Two-variable notation. We talked about this on the tail end of yesterday's class. going from two variable notation to function notation, and we're now saying that this is in fact a function, and we want to show people this. What is the distance dependent upon? Time. So we always go, I'm going to shorthand distance into the variable d. So distance is dependent upon, we'll put it in little brackets, t, and then we basically write out the rest of our formula. 700 minus 100 t. This is now function notation. The book likes to give you guys, they'll write it in a certain way that if you're not familiar to, it looks kind of weird. But they're going to say, or ask you a question like, you know, what distance are you at after, we'll say, 4 hours? And sometimes they'll have different ways of writing this out or explaining it. Basically, that 4 hours, you're going to have the distance. We know the distance is based upon time. So the distance at 4 hours. So that little 4 goes in for the d. And then wherever you see t, we also put in a 4. Equals 700 minus 100 times, our new time is now 4. What's 100 times 4? 400. And so our distance at 4 hours equals 700 minus 400 would be 300. They do this for a few reasons. One, if you're looking back, it'll tell you this distance. It tells you what variable you punched in for t, in our case 4, and go on from there. Who has a job? How much do you make? $13.85. So we're going to say your wage is equal to $13.85 an hour. However, because we like you, when you show up to work, they're going to give you a $10 bonus for showing up. Because why not? Okay? What kind of notation is this? Two variable. Okay? Please write it in function notation. Take 2 seconds. Okay. Written as function notation, your wage is dependent upon the hours you work, and everything else, you write the exact same. $13.85 times our h plus 10. When you have a formula like this, you can then punch in whatever you want. So let's say you worked an 8-hour shift, okay? Your wage dependent upon an 8-hour shift is $13.85 times 8 plus 10. So $13.85 is $110.80. We add 10 to that. So after an 8-hour shift, you're going to make $120.80. So, bit of a jump now. Remember way back, and I said there's a special case when you're graphing. Whenever we see the term evaluate, we're always talking about solving. So I want you to evaluate the function f of x equals 5x plus 4. Remember that f of x is our special scenario, because this is indeed function notation. If this was two variable notation, this f of x would actually turn into a y equals 5x plus 4. When we graph this, for right now at least, we're going to pick 3 points on a graph. And when you make your graph, again, this is line paper, it's not graph paper, so I'm going to kind of eyeball this as best I can. but I'm going to go up by 5s. Like so. So last year in grade 8, or grade 9, sorry, you guys would have probably created some sort of t-chart or something where you pick a couple of x values, plug it in for x to figure out what y is, or vice versa. We're basically going to do that, but instead we're going to pick 2, 1, and negative 2. So first we're going to go f of 2, f of 1, and f of negative 2. So when we solve each of these, basically where you see 2, every time you see an x, we're going to place in 2. What's 5 times 2? 10. And what's 10 plus 4? 14. So when f is 2, we know that f of x equals 14. When f is 1, what's 5 times 1? 5, and then 5 plus 4, we have 9. And again, 5 times negative 2 should be negative 10, and negative 10 plus 4, what is it? 6, right? Or negative 6. We now have each of our points. We've given you a x value and a y value. Now we can graph it. We have x's and your y-axis. So for the first point, when x is 2, roughly here, our y is positive 14. About there. When x was 1, y was 9. When x was negative 2, our y was negative 6. And again, this is not graph paper, so we're only going to be so accurate, but for the most part, it's safe to say that is our graph function. And the special scenario, especially the book, we're going to make f of x equal something. So if we look at that first example, we have f of x equals 5x plus 4. And we solved it when we said, okay, well, what's f of 2? We plugged in 2 for x, and away we went. The book, and you're often going to be asked, well, what happens when f of x equals 24? This is very different. We no longer plug in 24 for x. That's the wrong thing to do. We're saying f of x, or y, equals 24. And you have to solve for x. So what we do then is we then go f of x equals 5x plus 4. However, f of x is 24. So we're going to say 24 equals 5x plus 4. You're then going to use algebra to solve for your x. Okay? When using algebra, you basically go in the opposite order. So we don't want to divide by 5 first because it's being multiplied by x. So what we are going to do is take away 4 from both sides. 4 and negative 4 will cancel out. What's 20 minus 4? Or sorry, 24 minus 4? 20. That's going to equal our 5x. Again, our goal is to isolate x. What's the opposite of multiplying by 5? Divided by 5. Whatever we do to one side, we can do the other side. 20 divided by 5 is what? 4. So I know that when f of x, which is really just y, equals 24, my x variable would equal 4. So if you'd actually graph that in our last graph, x would be somewhere over here, and 24 would be way up top. But it should still be on our line. Good. At this point in time, we're done for the day. Your homework is on page 272, questions 14, 15, 18, and 19. That's it. You even see that, can you? Let's go down here. Try that.